We're going to be looking at chapter 2, the one that's called bell-shaped data. Today, my goal is to go over these 5 things. We're going to look at how to calculate the mean, which we kind of already know, but we're doing it again. We're going to look at a new thing called standard deviation and how you can calculate it. It's either called S, a capital S, or a lot less in textbooks, or sometimes it's called SD for short. So it depends, if you go looking at another video or something, they might call the standard deviation SD, short for standard deviation. And then we've got a thing called variance, which is typically called S squared, but they may have other names for it if you go looking. And then we're going to look at a thing called the empirical rule, and it should be used only for bell-shaped data. I guess I should talk about what bell-shaped data is as well. And then hopefully we'll get onto standardized Z-scores, which is a number that allows us to tell how unusual a single piece of data is. And that is something that can be quite helpful when we want to identify outliers. We already have a way of identifying outliers. Remember the rule about Q3 plus 1.5 IQRs. If you're bigger than that, you're an outlier. Or Q1 take away 1.5 IQRs. If you're less than that, you're an outlier. Well, there is another way that you can use standard deviation to tell if it's an outlier. And hopefully we'll get to that. So I've just created a random set of data. And we are going to find the mean. The usual symbol that is used almost universally is X with a little bar of it. So we're going to find the mean of this data. Now, it's a pretty small data set. I could simply just add them all up, right, and divide by how many. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, good, a nice awkward number. And 14, 15, 19, 29, 36, 56, 57, 67, 77, 80, 92, 97, 98. And 98 divided by 11. 98 divided by 11. And the answer, let's say, to 1 decimal place. So unless, the homework says to 3 decimal places, you round it off to whatever you happen to have. So there's our answer. Now, there's another guy called the standard deviation. And can you just trust me, you do not want to calculate this thing by hand. Even for a small set of data, it is ridiculously messy and big and awkward and long. And no one I know in statistics ever calculates the standard deviation by hand, even when it's a small data set. We always use software or a calculator. So rather than me tell you the formula for it, I guess I'll tell you the formula for it and then say don't bother about it. It's normally done in sigma notation. You don't want to do that formula, trust me. Would you agree you do not want to do that formula? So I'm just putting it there for curiosity reasons. So what does standard deviation measure? See, the mean, if you imagine this as a data set, right? So if you imagine this line represents the data, it starts at 0 and what does it finish at 23, right? And you've got, your data looks something like that, right? Big bumpy data. Doesn't the mean kind of tell you the typical person in the middle, right? It's a typical number, right? Standard deviation measures what's called spread. Spread is how far out is the data? Are all the numbers really close to 8.9? Are they all close to the middle, or are they miles away? So imagine I draw a little histogram, right? And can you imagine that's 8.9? So you can see here that most of the data is pretty close to 8.9, right? And then can you imagine another set of data? And can we pretend that's where 8.9 is? Can you see here that the data is much more spread out? In this case here, the standard deviation might be 3. And in this case here, it would be a bigger number, 5. So if the standard deviation is a big number, it's essentially telling you how spread out the data is. And if the standard deviation is a small number, it's essentially telling you that it's not that spread out. So if I, for instance, said to you, I got 2 classes, I'll call them Class A and Class B. And in Class A, the average in the exam was 50 and the standard deviation was 20. And in Class 2, the average was 50 and the standard deviation was 2. And if that's all I told you, can't you look at the standard deviation and say, the people in Class A, aren't their scores all over the place? I know the average was 50, but aren't you going to get people with 10 and people with 90? Right, it's all over the place. In this case here, because the standard deviation is a lot smaller than that, couldn't you say, okay, the average is 50, but in the Class B, isn't everybody very close to each other, right? There'll be a 47 and a 53, but not too much wiggle room, right? So if you're wondering what you're calculating when you calculate standard deviation, you are essentially calculating how spread out the data is. And since I've got my little data set and I've made a mess of it, I'm just going to rewrite it again. 5, 9, 1, 4, 17, 21, 23, 12, 5, 1, 0.
Hey, Professor Robertson.
Yes.
I found out how to get it to calculate on a TI-84. We just do that same.
Which is exactly, yeah.
Yeah. You do the normal thing.
Yeah,
we did the one var stats, or however you pronounce that. And one of the values it gave us is the deviation. That is exactly it.
Yes. Mm-hmm.
And then one quality of life thing, you can actually, there's a clear list button, so you don't have to erase everything in a list.
Oh, you are way ahead of the game. Cool. Right. We've done that. Let's show everybody what you're talking about. Let's get the standard deviation and then I'll show you the variance. That mess is saying standard deviation. Right. Now, if you hold on a few moments, I'm going to show you here we go. How we would calculate it using our TI-84. And with a bit of luck anyway, here it goes. So you're looking at the thing. The good news is you know most of it already. Can you remember that we used the calculator to find the 5-figure summary? Remember we did that? What Ashton was talking about is essentially that the same information is in that same place, right? We just need to show you it now. So this is kind of repeat, but we have to do it. We're going to first get the data in. So I'm going to hit start. I've got number 1, edit. And I'm typing in the data. Hopefully I won't screw up here. So it's 5, 9, 1, 4, 17, and 21. 23, and then 12, 5, and finish with a 1 and a 0. And you don't need to put. Yes.
I'm sorry.
You're talking.
I just got the calculator. This is Nakia. How do you get to the L1, L2, L3 screen?
Oh, you hit the start button. So it's next to the alpha There, you got them? And then you choose
Okay. I
option one.
apologize for interrupting.
No,
Okay.
I need to be told things like that because sometimes I go quicker than I should. Right, are you happy about where that data came from? Right, how we got it in? And now what we're going to do,
I'm there.
right, what we're going to do now is you just put in rubbish numbers if you just want to test the buttons, right? Hit stats, and you're back to the same menu again, but now we're going to move from edit to calc. So I'm moving over to calc. And the one that we want is choice number 1, which is where it is, 1 variable statistics, and I hit enter. In the newer calculators, you've got a little, it's like a little menu and it's got L1 on it. So in your case, you just hit enter a lot of times. On my case, I have to tell it L1. And the way I do that is blue button, number 1. So show you that again. You hit stats, go over to calc, choose number 1. Ooh, wait a minute. Let's clear that out of the way in case I confused it. Right, start, calc, choice number 1, blue button 1. And when I hit enter, lots of things appear. Can you see the 8.9 that I got by hand up the top there? Now, that guy there you don't care about, that guy there you don't care about. Do you see there's 2 funny looking guys, one called SX and one called Sigma? That symbol's Sigma, by the way. The guy you want is SX. So that's what the calculator calls it. It's the standard deviation of the data. And to 1 decimal place, because that's all I'm working with, it's 8.2. Does that seem reasonable? You know, it's not too many buttons to press. We feel good about that? Right, so what I'm going to do now is return back to the white screen and show you the rest of what we're going to do. We have got... yes.
You're in the stat screen where you can click edit. There is a clear button and you'll put in your list again so you won't have to erase every single digit.
I do know that button. I'm not going to push that information because it's dangerous, because if you do it the wrong way, you can actually delete L1 and it's a pain to get back. But if you're comfortable with it, go ahead and do it. I would just be careful.
Yours is kind of weird then. Mine only erases the individual numbers inside, not the actual top piece.
It won't, you're right, unless you go to the top piece and do it, in which case it might well delete L1. It's where you delete it.
I think we're both confusing each other, but let's just move on anyways.
Yeah, let's move on. We have 8.2. We got that. So who's this guy called variance? He's S squared. Funny name, until you know what he is. He's 8.2 times 8.2. So you just square that guy. And if we're sticking to the 1 decimal point rule, it rounds off to 67.2. Standard deviation and variance both basically do the same job, right? I mean, one of them is just the square of the other. Variance doesn't really get used that much, but occasionally it does appear in some advanced statistics where it is used to measure essentially how variable data is, hence the name. So are we comfortable that if I gave you a set of data, you could find the mean, you could find the standard deviation, and if you were being asked it, you could also get the variance? Does that seem good? Right. So let's look at some special cases. Here's an interesting set of data, or a boring set of data, depending on how you look at it. All the numbers are the same. I don't need a calculator to answer any of those questions. Would you agree that the mean is going to be 5? Right? If all the numbers are 5, isn't the mean 5? Maybe less obvious. What do you think the standard deviation is if all the numbers are the same number?
0.
Intuitively, does that make sense? There's no variation at all there. Would you agree that all the numbers are the same? And of course, if that's 0, won't that be 0? Agreed? Now, here are a very, very simple data set. The numbers 1, 2, 3. Would it be okay for me to say that the mean is 2 and it's pretty obviously 2? You agree? I wouldn't be able to really predict the standard deviation or variance, and that's fine. I'm going to nip over to my calculator right now and find out what they are. And the guy that we have got is 1, 2, and 3. So although you can't see me doing this, can you just pretend that I was doing it with you? Now I'm going in and I'm calculating it.
Shouldn't the standard deviation just be 1 because it only goes up and down by 1?
You would think so. It's a little bit messier than that, unfortunately, which is why
Oh,
I have
just
to
did it on my
calculate.
calculator and it is 1.
Oh, well, that is just sheer coincidence. I would say. Let's see. It is 1. Okay. I'm not arguing. It is 1, so it is 1. This is what I'm getting at in this question. Here is the same set of data, and all I have done is double all the numbers. Right, so instead of 1, 2, and 3, it's 2, 4, and 6. So the mean is going to be 4 now. You see the change? Does that make sense that if you double all the numbers, you're probably going to double the value of the mean? What do you think the standard deviation for 2, 4, and 6 is? And I'm not going to commit myself here because I was wrong the last time, so I'm actually going to do it while you're thinking. Do you think it's the same? Bigger, smaller?
The deviation is 2.
So this doubles. This doubles. And uh-oh. What happens to the variance? Won't it be 4? So what we're trying to get out of that. Imagine I have a set of data and the mean is 10 and the standard deviation is 5, right? So I've got 2,000 numbers and I got really lucky and the mean was 5 and the standard deviation was 5. And I took those numbers and I multiply them by 3. So you can imagine all the numbers now get multiplied by 3. The new mean will be 30 and the new standard deviation will be 15. Does that make sense? That if you take data and you transform it by just multiplying, don't you multiply these guys by that same amount? So can you imagine that you measured a whole load of information in inches and you wanted to send that information to someone in France? They probably wouldn't like inches. Would you agree? They would like centimeters. Well, all you would do is when you take your data and put it in some software and say, multiply everybody by 2.54, because that's how many centimeters in an inch, right? And that would do the job. Can you see that the data changes accordingly? Here's a different story. Imagine I have a whole set of data and the mean is 10 and the standard deviation is 5. But all I do is add 3 to all the numbers. Right, so your data, let's pretend your data is like 1 and 7 and 15 and 9 and 3 and 8 and so on, right? And I add 3 to them all. So that turns into 4, that turns into 10, that becomes 18, that becomes 12, that becomes 6, that becomes 11, right? So that's the old data. This is the new. We can actually predict the new mean and standard deviation. And I'm giving you a little warning here. Be careful. Okay, what do you think the new mean is going to be if you take all of these and add 3 to it? The old mean was 10. What do you think the new mean is going to be? I've got you worried now by saying be careful. Be careful doesn't mean don't answer. It just means be careful. What do you think it might be? Even if you're wrong, it's fine.
Would it be 13
Well done.
or no?
Now be extra careful. What do you think the standard deviation is going to be?
Wouldn't it be the same technically?
Yes. If you add 3 to numbers, basically, aren't you just taking all the numbers and shifting them a little bit? Won't they still be as spread out as they were at the start? So what this is telling us is that multiplication will affect how spread out the numbers are. Because if you multiply everybody by 3, don't you kind of spread them out 3 times as much? Right, because all the differences are 3 times bigger. But if you just take some numbers and add something to them, basically aren't the same numbers going to be the same spread? They're just moved a little bit, but they're all moved the same amount, so the spread's the same. So multiplication changes both. Addition only changes the mean. And that's pretty much all I want to say about mean, standard deviation, and variance. Do you want me to do another calculator version just to show you the buttons to press, or do you feel you're comfortable about how to do that?
I'd like another calculator version, please.
Okay. Okay, since you're asking, you're going to supply the data. Just randomly give me about 6 numbers. Whatever comes into your head, just shoot them out and I'll write them down.
5, 12, 21, and 3. Do I
Okay.
need one more?
So we are going to find the mean, standard deviation, and variance of that set of data, right? And we're going to do it on our calculator. So I'm going to leave this window, go into the other one, and we'll hit the buttons. And here we go. And I'll show you what Ashton was talking about, or at least my version of what Ashton was talking about. And then I'll show you why I don't like people using it. Okay, let's clear this out of the way. I'm going to hit start and I'm going to go into edit. Now, do you see I've got the old data, right? Now, this is one way of doing it. If you scroll up to the top where it says L1 and you hit clear and enter, it'll clear the whole thing. Now, it might not be what Ashton was talking about, but that's what I was talking about, right? And that's kind of
Yeah,
useful.
that's not what I was talking about for it.
But it does essentially the
If
same
you push stat,
job.
select clear list.
Ah, okay. That's another version, right? So clear
and
list.
you do second list 1, and it will erase all of the values inside of the list, but not the variable it uses.
Okay, so me and Ashley were talking about two different things when we were talking about clear list. And that one there is totally safe. You can't screw that one up. So let me go back in and show you the problem I have with the other way of doing it. If you go up to the top, you hit clear and enter, it's fine. But some people forget it's clear and they think it's delete. And I'm not going to hit that button, because if I did hit the delete button, the guy called L1 would disappear. There would be no more L1. And it's a pain in the butt to get it back. And a lot of students then email me and say, I've lost my L1 and my L2 and my L3, and now I can't do anything and help, and I'm panicking. So that's why I don't like it. But if you want to use that clear list, which is a totally different thing, then we are good about that. So I'm clearing that out the usual way. So back to your original, put in the data. There's a 5, there's a 12, there is a 20, there's a 1, and there's a 3. So we type in the data and we're good. I hit start. I move over to the calc. It's already set up with number 1, which is what I want, 1 variable statistics. Blue button 1 and enter. And in this case, the mean is 8.2. The standard deviation is this one here. Try and remember it's the S one. If you do it to 1 decimal place, it's 7.8. And then I'll come out of this and I'll do the variance to complete the set. And I'm just going to go 7.8 and square it. And I get about 60.8 if you round it off. Okay, do we feel comfortable now about just the number crunching, how to get mean, standard deviation, and occasionally, just occasionally variance? They don't ask that so often.
I'm still a little confused on how the calculator works. How to get it from the calculator.
Okay, what part of what I was doing do you want me to kind of say again? Let me do it this way. You hit the start button and you go to edit and you press enter. Are you comfortable about how to get to here?
Yes.
Okay, and then you type in all your numbers. Are you happy about doing that?
Okay.
Right, are you?
Yeah.
That's okay? Right, so the next stage is the last bit then.
Mm-hmm.
You hit the start button again. Done.
Okay.
You're looking at a menu that looks like this. You move this little cursor here, see this little guy here, and you move him over to
I
calc.
still see your face. Just the.
What a scary thought. I apologize. There we go. I'm doing this, the early bit really quickly because you said you were okay with that. Start, edit, type in your stuff. Start again, move over to the calc. It's on number 1, so that's good. So just hit enter. And then the blue button, 1. That's how you get L1. And then you hit enter. And everything you need for today is on this page here. So the mean is that top guy there, the 8.2. And the standard deviation is that SX guy, which is about, what, 7.8.
Oh, okay, I got it now. Thank you.
You got it? I do like it when students tell me that, because I can guarantee there's a couple other students saying, I didn't catch all of that, he was too quick. Right. So let's return and look at the next piece of the puzzle. The empirical rule for bell-shaped data. Good. That's a mouthful. Well, let's talk about what is bell-shaped data. What does that term mean? If you collect a lot of data, it's hard to tell when it's only a small list, but when you collect hundreds and hundreds of data points, they become quite cumbersome to just show people the numbers. So what you very often do is you make pictures of them. The kind of pictures would be things like histograms or dot plots. Okay, so can you imagine I did a dot plot and the data looks something like this. If the data looks like a hill, that's what a bell-shaped data looks like. Now, it's not a perfect hill. There might be a little bump on one side. There might be a little bit extra on the other side, but pretty much a single hill. In the middle is the highest, and then it drifts at the end. You get that kind of visual shape of a hill. They could have called it a hill-shaped data, and I think that name probably would have been a better name, but they call it a bell-shaped data. I guess because it does look a little bit like a bell, doesn't it?
Bells flare out at the bottom like that, kind of.
Yeah, so it's not a bad name, right?
Is there a test
So
to tell
what
if
isn't
something
a
is a bell shape in particular?
There is, but you don't know about it, and you won't be told about it. It's a statistical test. Nobody does it by hand. They just plug into the computer, and the computer comes back with a number. And as long as that number, it's a skewness number. As long as the skewness number is in a certain range, it's okay. You're never going to get perfect symmetric data. Bell shape just means it's a single one. So if I imagine a dot plot, can I draw that so I don't need to draw the little circles, right? That's just a shortcut. Now, that would be bell-shaped. Can you imagine data that had a big hill and then another little hill? That wouldn't be bell-shaped because it's got two hills. Agreed? If you had data that looked big high at the beginning and another big high at the end, that's not bell-shaped. Right? So bell-shaped data is a single hill, right? With a little bit of bumps at the ends of the line, but not major hills. Suppose the data was there was the same number of 4s, 5s, 6s, and 7s, right? So basically the data is a horizontal line. That doesn't count as bell-shaped either. So is it easy just to think of bell-shaped as it's a single hill? Right, that's it. If it's got 2 bumps or 10 bumps, or it ain't got a hill, or it looks like a big valley, I guess you could get data that looks like that, can you? It doesn't count, right? And what we're about to do is use a very special rule called the empirical rule. And this empirical rule only works if it's bell-shaped data. If the data looks like this or like this or like this, this rule does not work. So let's show you what it is. Can you imagine that we've got some bell-shaped data? Right? Nice hill. And I tell you that the mean of this data is 100 and that its standard deviation is 10. So We calculated it and we got really nice numbers. What does the empirical rule say? It says that the mean will be at the top of the hill. Does that seem reasonable, that that's where 100 probably should be? It says the mean is here. It then says, if you go 1 standard deviation, and then you go 2, and then finally you go 3, and then if you go 1 standard deviation less, that's 90, 1 standard deviation less again, and 1 standard deviation less again, you will create the following rule. 68% of all the data is within 1 standard deviation, 1 standard deviation of the mean. So from there to there, 68% of all the data. Now it's called an empirical rule, because what essentially has been discovered, that they've looked at bell-shaped data, lots and lots of different examples, right? Very tall hills, very squat, flat hills, and it ends up being that this rule is pretty resilient. No matter what kind of hill you've got, if you go 1 standard deviation either side, 68% of the data is in that range. If you then go 2 standard deviations, and I wish I had put that there now, so I'll do it up here. If you go 2 standard deviations, so that's from 80 to 120 in this case, 95% of the data will be in that range, right? So 95% of all the numbers are in that range. And last but not least, if you go 3 standard deviations, in this case from 70 to 130, so that's from there to there. I know it's a weird number, but 99.7% of the data is within 3 standard deviations of the mean. What that tells me is that if I have bell-shaped data, do you know the only 2 things I need to know about that thing is the mean and standard deviation? Because once I know that, I kind of know pretty much everything that's important. I've got a really good idea of where most of the data is. Kind of interesting. Now, remember outliers? Remember we talked a little bit about outliers? And there's a test for outliers that use these interquartile range. There is a test for outliers that uses standard deviation. And this is it. If you are more than 3 standard deviations, from the mean, you are an outlier. So if you want to find where do the outliers live, don't they live over here and over here? Isn't that number more than 3 standard deviations away from the mean, and this is less than 3 standard deviations away from the mean? Is that kind of cool that we've got another test for who an outlier is? Well, let's use this empirical rule. Suppose I've got a class and the average was 70 and the standard deviation was 6. And I'm going to do an outlier test. John got 80. And Mary, she got 40. And we'll have one more guy. We'll have Peter. Peter got 53. And we want to know if any or all of those people are outliers. Are they exceptionally unusual, right? Either exceptionally big or exceptionally small. Right? Okay. The mean is 70. If you add 3 standard deviations, you're going to get 70 plus 18, and that comes out to be 88. Okay. Now, if you go the other side, you do 70 and you take away 3 standard deviations. That's 70 take away 18, and that ends up being 52. Now, as you scan through these people, isn't John okay? He's not an outlier. Right? Don't you have to be bigger than 88 to be an outlier? Is Mary an outlier? Yeah. Don't you have to be less than 52? That's the other place. So she's an outlier. Is Peter an outlier? No. He almost, right? He was that close to being an outlier, but he's not. He's okay. Are we comfortable about this outlier test that we're using now? So if I give you a mean and a standard deviation and I tell you that the data is bell-shaped, do you feel comfortable about checking to see if a particular score or data point is an outlier or not, like I did here? You feel good about that?
Can you
Do
explain
you want another one of
why you chose
Yep.
35? Where did 35 come from for the 70?
Where's 35?
Is it 35, 70 minus 35 delta? What? I don't know what that is.
Oh, that looks like a 5 to you.
Okay, what is?
That's 3 standard deviations.
Okay.
It's a 3 and an S and a D. I guess I should put little things
I
there.
was confused.
Okay, I totally understand that because my 5s do look like S's. Don't they?
Okay, thank you.
Yeah. Does that help any? I'll try and remember to put the little dashes on
It
the
does.
S's
I
so
was
they stop looking like
racking
5s.
my brain trying to figure out what I was missing.
Well, I can understand why you would think that. All right. Are we cool with this, or do you want to see another am I an outlier question? You know, I have to rely on you because, you know, I'm not good at reading thoughts.
I'd like another example.
Okay. Oh, let's do IQ tests. Do you know that the average IQ is 100? You probably know that, right? There are 2 versions of IQ tests. There's the standardized IQ test, and I think the other one's got a French name, like the Pagenaud, some weird name, I can't remember. In this particular one, the standard deviation, I've made it look like an S, is 10. So one of the typical IQ tests is 110. That's kind of nice. The other, I think the French one is 100 and the standard deviation is 25, if you're interested. But that one's the typical one that if you did an IQ test, say online, just for fun and giggles, it'd probably be this one. Let's have Jasmine. And Jasmine took an IQ test. and she got 141. And we want to know, is Jasmine exceptional? Exceptional in this case, being an outlier isn't always a bad thing. Isn't being exceptional mean that you're world-class runner, right? Or you're really high IQ or whatever it might be. Being outlier isn't always a bad thing. So Jasmine gets 141, and we would like to see, is she an outlier? Because that's what exceptional is, right? Outliers, people who are beyond the normal range. Well, the test is the mean. In this case, it's a big number, so I'm going to do 3, and I think I'll just put the letter S this time, right? 3 standard deviations. In this case, the mean is 100. And 3 lots of 10 get me 130. So I want you to think of that as the last number that you're not an outlier. So outliers are bigger than 130. Doesn't Jasmine qualify then as an outlier? And we might put nice names like Jasmine would be considered a genius, right? According to IQs, right? Okay, let's have Donald. And Donald IQ is 72. Well, since he's a small one, won't we do the take away 3 standard deviations, right? We only need to look at what that one is. And this is 100, take away 30. And so we get 70 here. And is Donald an outlier? No, because I picked the question. I didn't want to insult myself too much. So my IQ is very low, but not at the point where it would be considered, an outlier. Are we comfortable about the test now? Did that help? Now, these numbers are not actually arbitrary. These numbers can actually affect you in all sorts of ways. Do you know the SAT test that you used to take before COVID got in the way? The SAT are done every year, and the SATs collect mean and standard deviations. And what that allows them to do is that universities, for instance, might decide if they're in a high demand area that you need a certain SAT score to even be considered to get into the program, right? So they, God, I wish I could say I remember, but I don't take SATs. It's an American thing. What's a going rate for an SAT? Well, does anybody know off the top of their head what an SAT score looks like? What kind of number?
I think the 1500 is the perfect score. So maybe
okay. So
1200 or 1000.
Right. So let's just pretend it's 1200, right? And I guess you could get all the way down to 0, I suppose. Okay, that still works. Let's say 1200 still is a kind of average kind of score, right? So, okay, for the sake of this question, there's a new test in Scotland called the Scottish SAT, right? And in the Scottish SAT, 1200 is the average SAT score that they get. And I'm making this number up. In the Scottish SAT test, the standard deviation is 100. And I'm picking nice numbers here. Now, if you were in a very high prestigious university and it was a medical school, one of the very cruel tests that you might do is that we only take people whose Scottish SAT scores are exceptional. In other words, we only take the outliers, right? We want the best of the best. So what would that mean in this case? Well, 3 standard deviations. They would be saying, don't even bother applying if your SAT score isn't 1500 or better.